All right, guys, today we're doing activity 21-1. It's going to be a pretty short lesson. As I'm talking, you can go ahead and pause the video if you need to spend more time doing whatever you're doing, calculating or whatever. So we are exploring exponential patterns. So I'll go ahead and read this first paragraph, and we're going to fill in the table. Raymond Hall, a graphic artist, needs to make several different size draft copies of an original design. His original graphic design sketch is contained within a rectangle with a width of 4 centimeters and a length of 6 centimeters. Using the office copy machine, he magnifies the original 4x6 design to 120% of the original design size and calls this his first draft. Raymond's second draft results from magnifying the first draft to 120% of its new size. Each draft is 120% of the previous draft. So complete the table with the dimensions of Raymond's first 5 draft version, showing all decimal places. So if we start with 4 and we magnify 4 by 120%, in our calculator we type 4 times, remember if I have 120%, if I move that twice, that's 1.2, so multiplying by 1.2, I get 4.8. Then I take that 4.8, that's going to get multiplied by 120%, or 1.2, to 5.76. I'm going to do the same thing for the other part. If the length is 6, that's getting multiplied by 120%, or being multiplied by 1.2. Go ahead and pause the video and complete the rest of the table. All right, this is what you should get. Let's discuss if we think this is linear. Do you think the width is linear? No, because you can see without even a calculator, this is going up by 0.8, and this is not going up by 0.8. So you don't even have to calculate all of them. If 2 of them aren't going up by the same addition or subtraction, it's not linear. Let's check out length, if we think this function is linear in terms of the number of magnifications we're on. It turns out this is going up by 1.2. Is this going up by 1.2? No, so it is not linear. It asks you to graph it, but I don't think we need to take time to do the graphs. I'll show you here what they are. This is basically your input, and this is your output. That's one function, and then this is your input, and this is your output for your other one, but they would give it different terms since we have x for both and 2 different y's. So this could be like f of n, or actually a better name would be w of n, the width in terms of the number of magnifications. This would be L of n, the length in terms of the number of magnifications. And here's your graph, which you don't have to do. So you can see it is not linear. It doesn't have a constant rate of change or increase. So your book's going to kind of talk through that, but we kind of save some time looking at that. Let's look at some other tables there at number 6. Explain why each table below contains data that can be represented by a linear function. Write an equation to show the linear relationship between x and y. So you want to look at first, what are we going up by? This is going up by 2, up by 2, up by 2, up by 2. Not all tables do that. If you look, this is going from 2 to 5, that's going up 3. This is not going up 3. So you have to be careful when you're looking at tables. So let's see if there's a constant rate of change in this first one. If it is, that makes it linear. And if it is linear, we of course can write an equation for that. So to determine if it's linear, we want to know if it has a constant rate of change. I mentioned this is going up by 2, up by 2, up by 2, up by 2. So this should be doing the same thing in the y direction. This is going down by 3, down by 3, down by 3, down by 3. So we know slope is the change in y, or subtract y's, over subtract x's. I can subtract any y's I want. Let's say I want to start with this y minus this y. -4 minus -1. Then I have to subtract the x's in that same order. 5 minus 3 minus a negative is plus, so that comes out to be -3. That comes out to be this. So the slope, this is my answer, but the slope is -3/2. So when I write my linear equation, that's going to be my slope. There are many ways to turn this into an equation. Maybe one way we want to go about that would be to insert a point. So here's a point. Of course, this is x and y. So I'm going to plug in my y is 2. I know my slope. The x value is 1. The only thing I don't know is b, the y-intercept, which I'm trying to find. So I'm going to solve this easy math equation here for b. So that's -3/2 times 1 is -3/2. Add 3/2 to both sides. So b is 3.5. I would allow an exact decimal for that. So then my final equation, y equals mx plus b. Okay, we've done this before at linear. You should know how to do it. Find slope. From there, you can do point slope if you like that better, or you can use slope intercept to plug in any point and slope and solve for your unknown. Remember, when making an equation, you should check your answer. So maybe try plugging in -1 to the equation you just made and making sure your output is fine. It's a great way to check anytime you're creating your own equations. Go ahead and pause the video and do B. When I'm looking at B, you gotta be careful, remember, because it's not going up by the same thing in the X direction. This is going up by 3. This one is going up by 6. This one's going up by 6. So you have to be careful. So what you should do is you should check the slope between these 2 points. Check the slope between these 2 points. Check the slope between these 2 and these 2. Make sure they all have the same slope. There are several ways you can do that. Of course, you can always do the formula, y minus y over x minus x. Take some time to do that. If you need to pause the video. Your slope should come out to 4/3. So now I need to write my equation. The easiest way for me to do it is to pick a point, my y, plug in the slope I found, plug in the x according to the point I picked. The only thing I don't know is b, so I'm going to solve this for b. So subtract 20/3. That's 1/3. I combine my slope and my intercept to make an equation. Y equals mx plus b. Because this is a fraction, this should be a fraction. We don't want to mix fractions and decimals within the same equation. So this, like I said, this lesson is pretty short. It's just looking at a table and determining if it is an exponential pattern, like this first one was. It was not linear. We multiplied by 1.2. We didn't add or subtract, so that is an exponential pattern, which is why our graphs are exponential. We'll get into that more in the coming lessons. And then another part of the lesson was looking at linear equations, like we did in 6. And if it is linear, to write an equation for that. Let's look at 7. Consider the data in the table below. Can the data in the table be represented by a linear function? Explain why or why not. Okay, so they set up some nice x's. It's going up by 1, so it should be very easy to tell without doing much calculating. The y should be doing the same thing since the x is increasing by 1. This is going down by 12. This is going down by 6. Definitely not linear. You don't have to take time to describe that, but you can pause the video if you'd like. B, describe any patterns that you see in the consecutive y values. Consecutive is next here, so 24 and 12, 12 and 6, 6 and 3. What do you notice about that? Each y is half of the previous y. Definitely not linear. So we're not going to write a linear equation. We're actually not going to write equations for this yet, but eventually we will get to writing equations for linear and for nonlinear. Your homework is pretty much to look at tables or information, sentences, and determine if that would create a linear function or not. So here's your homework. Go ahead and work on that. Let me know if you have any questions.